We also have depth first, right? This is going to be the opposite, right? Remember, we start at our node and we move across, right? Breadth first, going across the tree. The other option is to start at your root node and go down, right? And that's going to be your depth first approach. So depth first traversal considers a path all the way to a leaf before it says, hey, let me double back, let me see what else I can do. Okay. So here's your full algorithm. We are not going to have to worry about the things in brackets. Remember, the things in brackets are optional. And for us, we don't have to worry about this. We don't have to worry about this. We don't have to worry about this. You could do it. You could do that check, but that's the more general form. So for all children of the current node, recursively visit the left children and then recursively visit the right children. It's that simple. Recursively, though? What's that mean? So let's talk recursion. What is recursion? Recursion is a function which is defined in terms of itself. This is the mathematical definition. Okay, it's a function that calls itself in our programming terminology, and it's really useful to be applied to a fractal data structure. Like I talked about earlier in class, this is not like an official term, but it is a good way to think about things, right? A data structure where sub-aspects of the structure can be considered complete versions in their own right. In the same way that if you have a singly linked list, right? And this is the entire list, but then you just grab this part, right, from the index 1 node on, that is still a complete linked list. Okay. So structures where you can do that, recursion is real useful for. The upside is that recursive methodology is going to obviously be useful in that sort of recursive structure. Like there's a reason why the term is used that way. So how do we define a recursive function? This becomes the next question. What is a recursive function? Well, recursive functions are defined by so the question becomes, how do we define a recursive function? What are the elements of a recursive function? And our recursive function, one more time. So the question becomes, how do we define a recursive function? What are the elements of our recursive function? And recursive functions are defined by two elements and are determined by an if statement, right? They're separated by an if statement. So we have a base case, which is the most elemental condition for the function, right? It is the thing that we are trying to get to. It is the trivial case. And we have a recursive case where the function calls itself. And the goal of the recursive case is to move towards the base case. So these are the two aspects of it. Functions can sometimes have multiple base cases or multiple recursive cases. There's nothing against the rules about that. So let's do an example. Let's do an example of this where we have a simple base case, and a recursive case that moves us towards the base case. So let's define the classic recursive example function. Let's calculate factorial, right? And we're going to define it this way. Okay, and remember, factorial is this, and it equals 5 times 4 times 3 times 2 times 1. Okay, that is the definition of a factorial. It is the number that you start with times 1 minus that number over and over again until you get to 1. So what is our base case? What is our simplest case? And I know that you are probably thinking, well, if x equals 1, right? That seems to make sense. But actually, factorial functions are defined for 0. So when we say factorial is 0, we return 1. Right? Otherwise, we're going to return x times factorial of x minus 1. So if we say factorial 5, we're going to return 5 times fact 4. Right? Now, if we wanted to, we could have an elif here. Right, return. That would be legal too. It's unnecessary, right? Because this case will take care of this case, but it's totally legal. But you can see how with every call from this factorial function, right? It's 4, and then the next time we're going to get fact 3, then we're going to get fact 2, then we're going to get fact 1, then we're going to get fact 0, and here we don't call anything else. And so we start returning values, right? This return is going to be crucial. Both of these returns are crucial because we need to be able to return values from both cases, right? We are trying to calculate this value. If you have trouble with your recursive function, if you're like, hey, I don't get anything out, check for this. Check to make sure that you're returning your recursive case. We can do this in a main function, or we can do this in a recursive helper function. There's this idea of a recursive helper function as well, where we can say, hey, what about this? We're going to define factorial as taking one parameter. And then we're going to create our helper function. And it's going to take 2 parameters. And it's going to take, oh, I'm missing a colon here. That's okay. It's going to take the value we're trying to calculate currently and our running product, right? So now our base case is if x equals 0, we're going to return n because that's our running product, right? Our recursive case is going to be subtract 1 from our current functional number and generate our product as needed, right? And now you can see here we're going to get fact 5, fact 4, fact 3, fact 2, fact 1, right? And then we're going to hit here, and it's going to return our value, and it's going to return what 5 times 4 is 20 times 3 is 60 times 2 is 120. It's going to return 120, and then this will return 120, and then blah, 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 blah. We'll get all the way out to here, and this will also return 120. So these are two different approaches to recursion. And you can see in other languages, and hopefully you'll talk about this some when you get to 325, paradigms of programming languages. Python doesn't utilize this, but these two approaches are different in that this guy does all the returning at the end, if you notice. right? This guy just spits out this number at the end. It doesn't calculate anything on the way out. I suppose the other one goes 5 times fact 4, which is really 4 times fact 3. This guy's got to return all these states and put everything back from the call stack. Okay. So this is head recursion because it does all the calculation on the way in, and tail recursion because it does all the calculation. I'm sorry, I've got that wrong, and I always get this backwards. Right? So this is tail recursion. This guy is tail recursion. Right? Because the factorial, the recursive call is at the end. Okay. And some languages, this makes a difference. Some languages, tail recursion is better than head recursion. Python is not one of them. Python does not optimize for tail recursion. But that is something that you, in a lot of languages, including Java and C, doing this approach is going to be a little better. For you guys, I introduce it just because sometimes it's easier to think of this. Okay? I will tell you that you're more than welcome to use helper functions, even if it's just for interface purposes. So, any problem that can be solved with iteration can be solved with recursion, as we talked about. No structural benefits to one or the other. Some problems are more naturally inclined towards recursion, right? And those are going to be things like divide and conquer, where you're dividing your set in half. Typically lean towards recursion. Also algorithms with data structures that are that kind of recursively defined, that fractal design, recursion is useful for. So the downside to recursion, though, is that it's more computationally intensive. The method calls are slower than simply iterating variables. This is because you have to add and remove variables from the call stack, which is a slower process. So this is why divide and conquer algorithms are generally the preferred methodology for recursion. But when it comes right down to it, just being able to understand your approach better, as long as it's not too computationally intensive, is good enough reason. So if it makes your approach easier to understand, that is justification enough to use recursion in your algorithm.